Hello. In this lecture, we will be talking about the void fraction and pressure drop models for gas liquid flow in microchannels. The two quantities, the void fraction and the pressure drop or the pressure gradient in the channel, are of engineering importance. They are required to design any engineering device. So, it is important to develop correlation and get an estimate to for the pressure drop or void fraction in the channel. In conventional channel or in large diameter channel, a number of correlations, most of them empirical, have been developed to measure pressure drop or calculate or predict or estimate the pressure drop as well as void fraction in large channel diameters or large diameter channels. Now, the first thing that one would like to do is look at the applicability of these correlations which have been developed for large diameter channels, and then one would ask a question that is those correlations which are working fine for large diameter channels, are they good enough for small diameter channels or any modification to them is required. So, this is basically the theme of the lecture that we are going to have today. So, before going into this, we will first talk about void fraction, and then later in the lecture we will be talking about the pressure drop. So, void fraction, there are two different void fraction that we are talking about here. One is alpha and beta. As you see here that beta is homogeneous void fraction and alpha is the void fraction. Beta, if we know the flow rates of the two phases, then we will know beta, because beta is defined as Q gas over Q gas plus Q liquid. So, that means where Q is volumetric flow rate of phase I. Now, beta is defined as Qg over Qg plus Ql. So, if we know the flow rates of the two phases, then we know what beta is. Beta is basically the volume fraction of the gas if we assume that there is no slip between the two phases, if both the phases are moving with the same velocity. So, then the flow rates at which the two phases are introduced, they will move with the same velocity. Unfortunately, in most of the cases, it is not so. For example, Taylor bubbles, they move faster than the average velocity. So, there is a certain amount of slip in Taylor bubbles. Now, void fraction measurements is not an easy task to do. There are number of techniques that have been developed to measure void fraction in large channels, and more recently the techniques are being employed or being modified to measure void fraction in small diameter channels. So, some of these techniques are say for example, Bio et al. They have used simultaneous solenoidal valve. Mishima and Hibiki, they used neutron radiography apart from image processing. So, of course, image processing is one of the techniques that where one take a 2D image of the flow and then try to correlate from it to get the void fraction in the 3-dimensional channel. Okay. Then another method is electrical resistance method. So basically different phases will offer different resistance to the current flowing through it. So one can measure the voltage and then estimate the resistance, and based on that resistance over time, based on the resistance, one can calculate or one can obtain the void fraction at any cross section in the channel. Similar concept where one measures the capacitance in place of resistance is electrical capacitance method. Okay. So now let us look at the correlations. A number of correlations have been developed and it will be not possible to cover all the correlations in this lecture. We will be talking about those correlations. The correlations, most of them have been developed for large diameter channels and then they have been modified for use in small diameter channels. So one of the correlations or one of the class of correlations are Armand type correlations. So they are alpha is equal to some constant C into beta. Now if it is a homogeneous model, that means there is no slip between the two phases. That will be probably true when we have a very small size of the bubbles and then they follow the fluid flow faithfully. Then this C is equal to 1. So we have alpha is equal to beta. Now the next is Armand's correlation. So in this C is 1 over 1.2 or 0.833. 1 over 1.2 is nothing but 0.833. So in some places you will see that C is equal to 0.833, in other places as beta over 1.2. Okay. Now these two correlations or Armand correlation is quite widely used. So this is just saying, say for example for slug flow, that the Taylor bubble moves 1.2 times faster than the average velocity. Now another two correlations that have been listed here by Chisholm and Spading and Chen, they also use, so they have C, but C is not a constant, but C is a function of beta and the density ratio of the two phases. So they take into account the density ratio and beta for both the phases. So these two correlations one can look at in any standard book on multi-phase flow or in the literature in different papers. So then another class of correlations is Butterworth correlation, in which the void fraction alpha is defined as 1 over 1 plus a, where a is a constant, into 1 minus x over x raised to the power p, rho g over rho l raised to the power q, and mu l over mu g raised to the power r. I have tried to be as accurate as possible, checking these correlations again and again while typing, but however there might be some errors which I could have overlooked. So I suggest that when you use these correlations, please verify these correlations with the literature. You can find most of them in the two-phase flow, boiling and condensation in conventional and miniature channels by Professor Mustafa Ghesian. Most of the discussion that we are doing here, you can find that in the book. So for the homogeneous model, again if we define A, P, Q, R, all of them equal to 1, then one can end up with having a homogeneous model, which will basically be alpha is equal to 1 over 1 plus 1 minus x over x rho g over rho L into mu L over mu g. So basically here R might be equal to 0. So this term will go away. So one can check and find out that alpha is equal to beta. Now x is a new term here, but it is not new for most of us. X is quality, and as beta is volumetric homogeneous void fraction or the homogeneous volume fraction, and x is homogeneous mass fraction. So as x can be defined as m dot gas over m dot gas plus m dot liquid, where m dot is the mass flow rate of a phase. Okay. So then in the GV model they have assumed, or they have found that A is equal to 1, P is equal to 1, Q is equal to 0.67 and R is equal to 0. So they do not have any dependence on viscosity. Please check this. Okay. Now the Turner and Wallis model have A is equal to 1, P is equal to 0.72, Q is equal to 0.4 and R is equal to 0.08. Lockhart-Martinelli correlation, A is, unlike other three correlations, A is 0.28 here, and as you see other two correlations later also have value of A is equal to 1. So out of all this, only Lockhart-Martinelli correlation has A is equal to 0.28, P is equal to 0.64 and Q is equal to 0.36, R is equal to 0.07. So if you look at these correlation, all three of them, both of them have the value of P about 0.7. Then Thom's correlation, P is equal to 1 and Q is equal to 0.89, R is equal to 0.18. So slightly stronger function of viscosity ratios. And then Barkhoudji's model, P is equal to 0.74, Q is equal to 0.65, in this Q is equal to 0.89 and R is equal to 0.13. So there are basically different models and they have been grouped together as Butterworth type correlation. So we have looked at Armand type correlation, which is relatively simple. A is equal to C beta form, where beta is the volumetric flow rate. In this case, volumetric homogeneous volume fraction, whereas in this case we have alpha is equal to the function of x, which is quality, the density ratio and viscosity ratio. You might notice that the density ratio will be of the order of 10 to the power minus 3 and viscosity ratio of the order of 10 to the power minus 2 or 10 to the power minus 1. So the third correlation is CISC group correlation. So it has again a similar to Butterworth type correlation, that it uses quality. 1 minus x over x is one group that they use, then rho g over rho L is another group. So same the density ratios and the ratio of fractions, mass fractions of the two phases. Now then they have 1 over 1 plus s, where s is slip ratio, which is the ratio of the gas and liquid velocities. So, most of the equations that we see here are to model this slip ratio between the two phases. So, S is equal to 1 plus B1, we have two constants here, B1 and B2, and Y is nothing but it has been defined as 1 minus beta over beta, where beta is the homogeneous volume fraction or homogeneous White fraction. With some simple considerations, one can always find a relationship between the mass volume fraction or homogeneous mass fraction, or not mass volume fraction, mass fraction. So, one can find a relationship between X homogeneous mass fraction and beta, which will also involve the density of the two phases. So, I suggest that you should do this as an exercise if you are already not, if you have not done it earlier. Okay. So, S, the slip ratio, is a function of 1 plus B1 into this term, which has B2 and Y. Y we have already seen. So, now what needs to be found is B1 and B2. So, they have defined B1 based on the liquid only Reynolds number and the density ratios. Now, ReLO is liquid only Reynolds number, and we will be using this quite often. In this lecture. So, this is defined as ReLO is equal to channel diameter divided by mu L rho L into UL or liquid velocity, or you can define as D is equal to D into GL over mu L, where G is the mass flux. So, basically ReLO is the Reynolds number if only liquid phase would have been flowing in the channel, and B2 is equal to 0.0273 Weber number. So, if you do not remember Weber number, let us just remind ourselves that Weber number is rho U square over sigma over D, because it is the ratio of inertial forces and capillary forces. So, it can be defined in this manner, then we will have the properties of and the velocities of liquid in this case. So, that is Weber number. So, if we look at this, in this correlation, the care has been taken to take into account the density ratio. We can see the density ratio in a number of places. It takes into account the viscosity of liquid using Reynolds number. It also takes into account surface tension using Weber number, and it takes into account the flow rate ratio of the two phases or the mass flow rate ratio of the two phases using X. So, this is a correlation which takes into account most of the physical effects that might occur. Now, surface tension is an important parameter which is there in the microchannels. It also takes into account the channel diameter by WeLO and ReLO. So, one would expect that this correlation might work for low Reynolds number, or not low Reynolds number, low diameter or small diameter channels. And so let us look at some of the literature that people have found. So in small diameter channels, for example, Bio et al. Have compared their results with CISC correlation for channel size ranging between about 0.74 mm to 3.74 mm. So from about 1 mm channel size of that order. And then they found that CISC correlation is suitable for their purposes. On the other hand, Triplet et al. They found that their data correlated well with homogeneous model in 1 mm size channel, except for annular flow regime, for which it over predicted. Now, an exercise has not been taken up to look at the CISC correlation, or at least I am not aware where an extensive comparison with the CISC correlation has been made with all the literature data for void fraction in microchannels. It would be really good to see if CISC correlation fits all the data well. Now, Chung and Kawaji and other co-workers, they have looked at the effect of channel diameter on the void fraction, and you see an interesting trend in these graphs. So there are 4 channels that they have looked at, or that they have been plotted. They have actually looked at more channels in other articles. So if you look at here, 530 micron channel diameter, 250 micron channel diameter, so this is 0.5 mm, 0.25 mm, 96, so about 100 micron channel diameter and 50 micron channel diameter. All 3 channels are circular amongst these, and 1 channel, about 100 micron size channel, is square channel. And they found that for the millimeter size channel, or so you can look at that y-axis is what is plotted alpha, and on the x-axis is the homogeneous void fraction, or beta, has been plotted. So they look at that homogeneous void fraction is good for 0.5 millimeter or 530 micron size channel. As the channel size decreases, the ratio between alpha and beta, it starts decreasing. So the slope of this line is decreasing, and then that is why they say that alpha over beta is equal to 0.833, which is Armand type correlation, or which is Armand correlation that predicted well. At lower correlation, they see a different trend, especially this is very clear at 50 micron channel diameter, that the ratio between the alpha and beta is small, and then it increases sharply at high quality or high gas fraction. So based on their results, and these plots have been taken from Gasian's book based on the work of Chung and Kawaji. So they have developed a correlation which is that alpha is equal to a constant C1 beta to the power 0.5 divided by 1 minus constant C2 into beta to the power 0.5, and this constant is sensitive to channel size. So they looked at for 50 micron channel, C1 is, sorry, this is 0.02 actually, 0.02, and C2 is equal to 0.98. For 100 micron and 96 micron channel, C1 is equal to 0.03, C2 is equal to 0.97, and in both the cases C1 plus C2 is C1 plus C2 is equal to 1. Okay, so this is one correlation that has been developed for flow in microchannels, and but this does not take into account the size of the channel explicitly. Rather, based on their observations from their experiments, they looked at that there are different values for different channel sizes. However, the difference between those is not very different, as you can see from here. Okay. Now, so they further developed that these constants they are sensitive to channel size, and then they developed a correlation C1 is equal to 0.266 divided by 1 plus 13.6 exponential minus 6.88 dH. So, where dH is the hydraulic diameter of the channel, which is the channel diameter if it is dH is equal to 4 into area of cross section divided by perimeter. So, for a circle this dH is equal to 4 into pi r squared over 2 pi r, r cancel out, pi will cancel out, and 1 will have 2 r. So, H same as the diameter of the channel. For a square channel, if d is the channel dimension, one will again get dH is equal to 4 into d square, where d is the dimension of the channel, into divided by 4d. So, 4 and 4 will cancel out, and one will get dH is equal to d, where d is the size of channel. For other channels one can similarly find out the hydraulic diameter. So, the correlation, the same correlation, but in this now C1 is a function of the hydraulic diameter of the channel, and C2 is 1 minus C1. Now, another correlation that have been developed to look at the effect of channel size is where alpha is equal to 1 over 1 plus C into x to the power a. Now, we have this x is not quality, x is capital X here, and now we have 3 unknown parameters here, C, x and a. So, x is known as Martinelli or Lockhart-Martinelli parameter, which is defined as x square is equal to dP by dz liquid, or you can say liquid only, divided by dP by dz gas only. So, dP by dz liquid only or dP by dz gas only are the pressure drops in the channel if there is only single phase flow. So, liquid only refers that if there is only flow of liquid, and gas only refers if there is flow only of gas. So, these are the frictional pressure drops which one can find using Poiseuille's law for laminar flow, for fully developed laminar flow, or Blasius's law for turbulent flows, which we will be talking about later when we talk about the pressure drop. So, in this correlation which was for the large channels, the Lockhart-Martinelli correlation, this it had C is equal to 0.28 and A is equal to 0.71, the C constant 0.28 and constant A is equal to 0.71. Turner and Wallace, they had C is equal to 1 and A is equal to 0.8. Now, Kawahara et al, they have modified this correlation to incorporate the effect of channel diameter in this. So, they had C is equal to 0.05 1 plus 55 exponential minus 60 over d star, and d star is a reference diameter which they took as 250 micron. So, this correlation has been modified again. You can say that this was Lockhart-Martinelli and Turner and Wallace correlation, which has been modified by Kawahara for implementing in microchannels. So, we have looked at that the void fraction measurement in microchannels depends on a number of parameters, or it might be the homogeneous void fraction or homogeneous mass fraction, then the density ratios, viscosity ratios, and the ratio of the two velocities, or the slip ratio and surface tension and the channel diameter. So there are some correlations which we have discussed, and there are some more correlations which we have not cited here, but people have developed those correlations, and most of those correlations are dependent on the data that has been generated by the authors, or some other data that they have compared their correlation with. But there does not seem to be an universal correlation which can predict the void fraction over all the channel diameters for all the fluids for all the flow conditions. This is largely due to that if one goes at lower channel diameters, for example 50 micron or lower, one sees that the contact angle effects become important there, which none of this take into account. Moreover, over a range of flow rate ratios, there is a range of there are different flow regimes that we observe, and in each flow regime the arrangement of gas and liquid phases is different. So the void fraction or the slip between the two phases is very different in the flow regime. So it is very challenging to develop a universal correlation which can predict all the data correctly. So now let us come back to pressure drop in microchannels, and this has been investigated by several co-researchers in the past 20-30 years, and many of them have compared the data with the correlation for the large channels, and most of them had only limited success. So the data has been or the correlations have been modified to fit the data, and rarely there is a well agreed correlation which can predict like void fraction. The same is the case for pressure drops, and there are number of uncertainties for pressure drop. For example, when one measures pressure drop, the flow will not be fully developed immediately. So one might need to take into account the pressure drop in the developing regime. So one should be measuring the pressure drop once the flow has reached at a fully developed state, and the pressure drop between those two, say for example in the test section, one can measure the pressure drop at these two regions. And it is not easy to have probes in a microchannel at such distances. Most of the times people measure the pressure drops at the inlet stream and then at the outlet or the outlet when it is open to the atmosphere. So then one need to take into account the losses that happens at the mixers or at the valves. So there exists uncertainty in the exit and entrance losses, and this is more dominant in microchannels. Then the wall roughness, if you look at the roughness, epsilon d is a length scale for roughness, and capital T is the channel diameter. And looking at the accuracy of machining and other or manufacturing, the epsilon d over d will be very small for large channel diameters. However, it will be not the case for microchannels. So the roughness might have a stronger effect, and one might need to take into account, so that epsilon d over d can have an effect. Channel geometry of course will have an effect on the pressure drop. Then it is also not possible to immediately extrapolate the correlations that have been developed for large channels, because the flow in large channels is often turbulent, whereas the flow in small diameter or micro channels is often laminar. So it is not possible to immediately or to use the correlations for large diameter channels as it is for small diameter channels. Okay. So, if one look at steady state, the pressure drop will be a sum of the accelerational pressure drop, the hydrostatic pressure drop because of the gravity, and the frictional pressure drop. So, the accelerational pressure drop is often important when one has phase change and the area of one phase is changing with respect to the other. So, it might be boiling or condensation. So, because we are talking about here adiabatic flows, so we will not be talking about the accelerational pressure drop. Hydrostatic pressure drop one can anyway take care by using rho g h, using appropriate rho here. Now, we will be talking about mostly the frictional pressure drop dp by dz. Some other pressure drops might come, say for example, when there is an abrupt change in flow area or flow path, or pressure drops in control or regulation devices, as we discussed in the previous slide. Okay. So, again for the pressure drop for two-phase flow, the correlations are generally based on the pressure drop for single phase flow, and from that the correlations have been developed. And the careful experiments in last past 10 to 20 years, it has shown that for 100 micron side channels or millimeter side channels, of course, one can use the correlations that have been developed for conventional channels. So, for the laminar single phase flow in a channel, those correlations are very well established for small diameter channels also, or they can be easily used. So, let us look at it that for a laminar flow in a channel, we have pressure drop can be defined as delta P over L is equal to 8 mu u over r squared. Now, the pressure drop in the channel is often defined in terms of friction factor, and there are two friction factors you might remember, and it is confusing most of the time that there are two friction factors. One is called Darcy friction factor and another is Fanning friction factor. So, the difference between them is the definition that they have. The one we have here defined as F is this is Fanning friction factor, and the Darcy friction factor is 4 times Fanning friction factor. So, one need to be careful that which friction factor one is using. So, the Fanning friction factor for laminar flow is F is equal to 16 by Re, and this can be if you substitute the delta P by L or dP by dZ, then one can find out F is equal to 16 by Re. And for turbulent flows, this is called Blasius correlation. And it gives F is equal to 0.079 Reynolds number to the power minus 1 by 4. So, these are the pressure drops relations for single phase flow. Now, because as we just talked about that the roughness might be important, so a correlation which has been used by several researchers to predict single phase pressure drop for laminar, transition and turbulent. So, basically all the flow regimes for single phase flow taking into account the roughness of the channel is called Churchill's correlation, and it has F is equal to 8. In this there are two constants, as you can see, A and B plus C1. So, C1 is 8 for circular channels, and A is again function of Reynolds number, the channel roughness, and CT, and CT is 1 over root CT is 2.457. So, this takes into account the roughness of channel, and B constant B is 37530 over RE whole raised to the power 16. So this correlation can be used to obtain friction factor and from there the pressure drop in rough channels for single phase flow. Okay. So like void fraction, the simplest thing is looking at a homogeneous flow model. So homogeneous flow model assumes that the two phases move with the same velocity, there is no slip velocity between the two phases are both well mixed, and so one need to take into account the only factor that what is the F there. F, as we will see, F is as we have seen, F is equal to function of RE. So I have just written G here because F is here. So F is a function of Reynolds number. Now one we will need to look at that what is rho and what is the mu that one should be using here. G, of course, or the flow rate or the velocity, one can use the mixture velocity. So the density, there are two definitions of densities one can use, that rho is equal to rho 1 alpha 1 plus rho 2 alpha 2, or as it has been listed here that sometimes this definition of rho is used, rho is equal to x rho 1 or rho gas plus 1 minus x rho liquid. This is harmonic average, mass fraction weighted harmonic average of the densities. Okay. Then there are different definitions for viscosities. Say one given by McAdams is mass fraction. So 1 over mu for two phase is equal to x over mu g plus 1 minus x over mu L, or volume fraction weighted average of viscosity. So one can have the viscosity, two phase viscosity is this basically will be, if we do not know alpha, then one can use beta here. So this will be sigma I rho I beta I, which is basically rho 1 beta 1 plus 1 minus beta 1 rho 2, and this 2 is liquid and beta is for gas, so we have rho gas. Okay. And mass fraction weighted average of viscosity, so where mu Tp is equal to rho gas x plus 1 minus x rho liquid. So different combinations of volume fraction or mass fraction weighted averages of viscosities and densities have been used to predict the pressure drop using homogeneous flow model. In my opinion, it is appropriate to use if the liquid phase is in contact, only liquid phase is in contact with the wall, then probably one can use the viscosity of water and try to see how well does it do for the correlation. Okay. Now for pressure drop, another very famous correlation, especially in large diameter channels, is known as Lockhart-Martinelli correlation, and then further down the constants in that given by Chisholm. So it is Chisholm and Lockhart-Martinelli correlation, and so it uses the concept of two-phase multiplier. So it gives that the pressure drop in two-phase is equal to a two-phase multiplier, which has been given as phi LO square. So liquid only into dP by dZ LO. One can also have dP over dZ two phase is equal to phi gas only squared and dp by dz for gas only. So, there are different correlations for this also. Now, the Martinelli parameter that we have already discussed for void fraction is the ratio of the pressure gradient if it is only liquid only flow and pressure gradient if it is gas only flow. So, the x square is the ratio of dp by dz liquid only and dp by dz gas only. Okay. So, once we have obtained Martinelli parameter, then from Martinelli parameter one can calculate the two phase multiplier, and remember this two phase multiplier is required to obtain the pressure drop in two phase. So, this is 1 plus C over x plus 1 over x square. Now, x is Martinelli parameter. So, we know this from here, and we already know how to calculate the dp by dz in liquid and gas cases. One can calculate the Reynolds number for liquid phase, for gas phase, and obtain and use appropriate correlation, either f is equal to 16 by Re or f is equal to 0.079 Reynolds to the power minus 1 by 4, the Blasius correlation. So, one would have obtained x from there. Now, the value of C. So, Chisholm he gave a table that for turbulent. So, T here stands for turbulent, and L is for laminar flow, and for turbulent flow the constant C is 20, for liquid laminar flow and gas turbulent flow it is C is equal to 12, and for turbulent liquid flow and laminar gas flow C is 10, and both laminar C is equal to 5. Now, the modification, there has been a modification for microchannels, and that says that C is equal to 21 1 minus exponential minus 0.319 dH, where dH is in millimeters. So, one has taken into account the effect of channel diameter into this. So, otherwise what we have is from this the effect of the flow rates of the two phases, the viscosity of the two phases, and the density of the two phases in these correlations. Okay. Now, let us just look at that can we apply this Lockhart-Martinelli correlation to obtain the pressure drop for a quality of 0.2 in a capillary of diameter 0.5 mm for air water flow. And we can take the density of gas is about 2.4 kg per meter cube. Density of water, let us take as 1000 kg per meter cube. Viscosity of gas is about 1.8 into 10 to the power minus 5 kg per meter per second, and viscosity of liquid is, which is water, so again 0.001 kg per meter per second. Okay. So, if we have to calculate the pressure drop in such case, we have been given the mass flux and we have been given quality. So, quality is 0.2 and mass flux G is 500 kg per meter square per second. So, we have G of liquid is equal to 500 into 1 minus 0.2, which is 400 kg per meter square second, and G of gas is equal to 100 kg per meter square second. Okay. So now to obtain two-phase pressure drop, remember the pressure drop that we will obtain using this is only frictional pressure drop. So that will be equal to phi, let us take liquid only square, so this is two-phase multiplier into dP by dZ into liquid only pressure drop. So first we need to find out the liquid only pressure drop, so we can calculate dP by dZ liquid only. Before that we need to calculate the Reynolds number for the liquid phase. So Reynolds number is D channel diameter, G liquid over mu liquid. So if we substitute the values, we will get 0.5 10 to the power minus 3 into GL is 400 divided by 10 to the power minus 3, and this will give us a value of about Reynolds number of 200. Okay. So basically the flow is laminar liquid flow. So we can say that for laminar flow dP by dZ is equal to 8 mu u over r square, and when we substitute the values, what we will get is 51,200 Pascal per meter. G one can obtain, or U, because U is not known, so U one can obtain by G liquid by rho liquid. You can say that this GL is kg per meter square per second, and kg is kg per meter cube, so the units will be meters per second. Okay. So we have obtained the pressure gradient for the liquid flow. Now x square, which is the Martinelli parameter, that is dP by dZ liquid only divided by dP by dZ gas only. So we need to find out the pressure drop in the gas phase as well. So we will need to find, that was Reynolds number of liquid, we need to find Reynolds number of gas. So that is again 5 into 10 to the power minus 3, which is channel, it's not minus 3, it's 5 into 10 to the power minus 4 into 100, which is the gas flow rate, divided by mu of gas, which is 1.8 into 10 to the power minus 5. So we get the Reynolds number of gas phase is about 2778. So let us make this calculations separated. So that is the calculation for Reynolds number of liquid phase, this is Reynolds number of gas phase, and from that, because this is more than 2100, so we will use the Blasius correlation. We will treat it as turbulent flow. It's not then we will have dP by dZ gas only is equal to 0.0792778 raised to the power minus 1 by 4, and that will give us a value of about 1.8 it's not dP by dZ, it is basically F frictional pressure drop. So once we have obtained this fanning friction, which comes out to be about 0.011, then one can calculate dP by dZ for gas only phase is equal to 4F, this is fanning friction factor, into G squared over 2 rho and channel diameter. So once we substitute here, we get 4 into 0.011 into 10 raised to the power 4, which is 100 squared, divided by 2 into rho is rho gas is 2.4, channel diameter is 0.5 into 10 to the power minus 3, and when we substitute this, we get a value of 1.8 into 10 to the power 5 Pascal per meter. So we have got the pressure drop in the gas phase, pressure drop in the liquid phase, and from that we have got x square, which is 51,200 Pascal per meter, divided by 1.8 into 10 to the power 5 Pascal per meter, and the ratio comes out to be 0.28, and we will get x is equal to square root of 0.28, which is about 0.53. Now we need to find out phi LO square or two phase multiplier 1 plus C by x plus 1 over x squared. So we know everything else, the only thing we need to know is C, and we have seen that C is equal to 21 into 1 minus exponential minus 0.319 dH. So C is equal to 21 into 1 minus 0.319 1 minus exponential minus 0.319 into 0.5. So one gets the value of C to be 3.1. Remember, this is in mm. So one gets the value of C is equal to 0.31. So phi LO square is equal to 1 plus 3.1 divided by 0.53 plus 1 over 0.28, and this comes out to be about 10.4. So dP by dZ for two phase is equal to phi LO square is 10.4 multiplied by liquid only dP by dZ, which is 51,200 Pascal per meter, or this is about 5.33 into 10 to the power 5 Pascal per meter. Okay, so that is the pressure gradient for two phase flow, and that we have used Lockhart-Martinelli correlation here with the correction by Mishima and Hibiki, I guess, which is for the value of C here. So I would suggest that you should be doing some of such exercises to obtain the feeling of numbers and to use these correlations to verify some of the literature data with these correlations. Okay. Another correlation which has been used in large channels is Friedel correlation, and there are two different correlations. One is for horizontal and vertically upward flow, and the other one is for vertically downward flow. I have not put it down here. So this expression, you see that the two-phase multiplier, so we are still using the same correlation like this, where we have to have a two-phase multiplier. So this two-phase multiplier is being defined by Friedel, which is 1 plus a plus 3.24, and it is a function of x and 1 minus x, where x is quality, then the density ratios, viscosity ratios, and Froude number and Weber number. So Froude number is ratio of inertia and gravity. So that is basically u square over GD, and one can use UTP here, and Weber number we have already seen, so that is rho u square d over sigma. Okay, and one can use UTP here. Okay, so in this correlation, the while the Lockhart-Martinelli correlation or the other correlations, they do not have the effect of surface tension, whereas the effect of surface tension has been taken into account in this case. And this might be a good idea to check the validity of Friedel's correlation for microchannels, which has been done by some researchers. Okay. So in general, the correlations that has been developed for large channels, they are not able to predict void fraction and pressure drop in microchannels as it is. Some modifications has been suggested. One of the flow regimes that is most important, or that has been used for almost every application of microchannels, is Taylor flow or Slug flow regime. So it makes sense to get the void fraction and pressure drop correlations for this flow regime. So we will just talk briefly about that correlation. Now for the Slug flow regimes, one can write a correlation between UTP. We have already seen it for when we discussed Slug flow or Taylor flow. So one can write a relationship between the bubble velocity UB into alpha, that is equal to UTP into beta. So if the bubble velocity has been measured or bubble velocity has been obtained, then one can obtain the void fraction, the void fraction, or in some places it is also called, we have termed it as epsilon g, the void fraction. So please do not confuse, it is same as we have used in the Taylor flow discussion. This void fraction is epsilon g. So this alpha is equal to UTP beta over UB. Now we have also seen a relationship between UB as a function of film thickness. That can be obtained as UTP into pi r square is equal to UB into pi r minus delta f squared plus U film, which is often neglected, into pi r square minus pi delta f square. or not, pi r square minus pi r minus delta f square. Okay, so one can obtain ub as a function of film thickness. Now we have a number of correlations for film thickness, the prominent or most popular of them being the Berthoudin's correlations 1.34 Ca to the power 2 by 3, and there is oscillation square modification which has been derived by class 4. So this is 1 plus 3 by 4, 1.34 Ca power 2 by 3 divided by 1 plus 3.34 Ca to the power 2 by 3. So one can use this correlation for film thickness, and from this one can obtain bubble velocity, and once one have obtained bubble velocity one can substitute here. Of course one will know the flow rate of gas and liquid, so one knows what is UTP and beta, and that is basically the superficial velocity of gas. So one obtain what is alpha. Now a small error in the film thickness, you can make this, you can test this for yourself, that a small error in film thickness can have a large error in the bubble velocity and consequently in the void fraction. Okay. Then for the pressure drop in the slug flow regime, we can divide, if we take a unit cell which consists of a gas bubble so if we consider a unit cell consisting of one bubble and one liquid slug, then we have there are different pressure drops that we need to consider. The pressure drop in the continuous slug phase, so delta P slug, then pressure drop in the cylindrical region or in the film region, because this flow regime occurs in gas liquid and liquid liquid flow. So one needs to take into, or one can make a generic or general correlation which can be valid for both the cases. So one can say that that is the pressure drop in the film region which will be negligible for gas liquid flow. And we have bubbles, and then the interface pressure drop, so the pressure drop at the front and back of the bubble. Okay. So it has been observed that if the slugs are long enough, then one can use the single phase flow. So let us remind ourselves that the slug have a velocity profile which is close to parabolic velocity profile here, and if except near the ends of the bubble. So one can use, for long slugs, one can use the Hagen-Poiseuille correlation, from where one can obtain that the pressure drop is 8 mu u L over r square, where C is the continuous phase, UTP is the two phase velocity, sum of the velocity of the two phases, and L is the length of the slug. So the pressure drop or the in the slug phase is given by this. Now pressure drop in the cylindrical region, one can assume an ideal smooth interface annular flow, which we will be discussing in a separate lecture. So from that one can calculate the pressure drop in the film region, and that comes out to be this for high value of lambda, where lambda is the droplet or bubble viscosity to continuous phase viscosity. So this can be negligible for gas liquid phases. And then the third is the pressure drop at the front and rear ends of the bubble. So it will depend on the curvature at the two phases. So if you consider the point here and point here, the pressure drop at the front, because the pressure in the gas is almost uniform, so the pressure, you can say the pressure in gas here and pressure in gas here is same. Now you can say the pressure at front and pressure at rear. So delta P, because of the interface, is delta P at the interface is basically PR minus PF, and that one can write that PR minus PG minus PR minus PG minus PG minus PF, or PR minus PG plus PG minus PF. So that we can give that the pressure drop at the front is 2 sigma, or one can have this as sigma kappa at the front, and this is sigma kappa at the rear. So based on this, one can calculate the pressure drop at the front and back, and using Berthoudet's model, following Berthoudet, this is the pressure drop that has been calculated because of the bubble. So if we sum these two, and this has been done by Crozier, and he has obtained a frictional pressure drop or the friction factor for two-phase flow in the slug flow regime, which is 16 by RE 1 plus A D, over where D is the channel diameter, L is the length of slug, and RE over CA raised to the power 0.33. And this value of A, what he obtained from his correlation, was 0.17, and then he compared this with the numerical simulations, and he found that 0.07 fit well his numerical simulations, whereas from experimental data it was 0.17. So this is one correlation which is used, or which can be used for pressure drop in the slug flow regime. Okay. So in summary, what we have looked at today is the void fraction and pressure drop correlations for large channels, and how they have been modified for small diameter channels. Please note that we have not discussed all the correlations that are available there in the literature for large channels. Neither have we discussed the correlations, all the correlations that have been developed for microchannels or that have been modified. All the modifications are there for microchannels. We have not put together all. The message is that one can modify these correlations and look at that what are the physical factors which are being taken into account into the small diameter channels, and try to see if a universal correlation can be there, which seems to be almost impossible to me. I would suggest some of you can take up the task of verifying the correlations, especially the ones which include all the effect of all the factors such as surface tension and the channel diameters. For example, the ones that come to my mind is CISC correlation for the volume fraction and Friedel correlation for pressure drop, and look at their validity for a large range of data, if that can be, those can be good enough for small diameter channels. Okay. And then we have looked at briefly the pressure drop and void fraction, how it can be measured for the Taylor flow regime. There has been some recent modifications in the in a recent paper by Classbor for pressure drop in the Taylor flow regime. So I suggest that you look into it, and that generally mostly talk about the pressure drop, the interfacial pressure drop that is there. Okay, so thank you.